Welcome back to the deep dive. If you are learning the fundamentals of pharmaceutical toxicology, well, this document is your foundation.
It really is.
Today, we are taking a deep dive into the ICH S2R1 guideline on genotoxicity testing. Our mission is pretty clear. We're going to give you the shortcut to understanding the core test battery. We're going to signpost those non-negotiable numerical limits for your exams, and maybe most importantly, we're going to unlock the crucial strategies for interpreting those tricky positive results.
That interpretation piece is exactly why this guideline is so important. I mean, S2R1 isn't just some regulatory checkbox.
Right.
It is the internationally harmonized standard agreed upon by, the three major global regulatory bodies, the EU, Japan, and the USA. It was finalized back in 2011, replacing and merging the older S2A and S2B guidelines.
Okay, so why the revision? What was the ultimate goal there?
The objective was, in a word, optimization. Regulators realized we needed a more efficient, yet still maximally safe approach.
So smarter testing.
Exactly. They wanted to optimize the standard genetic toxicology battery to better predict potential human carcinogenic risk, and also heritable risk effects rooted in changes to our genetic material. It's about being smarter with testing resources while always maintaining patient safety.
Hold on a second before we dive too deep. Who is this guidance actually for? I know it covers drug development, but does it cover, all new drugs?
That's a crucial point. No, this guidance has a very specific scope.
Okay.
It applies only to testing new small molecule drug substances intended for human use. So if you're working on large molecules biologics like monoclonal antibodies or protein therapies, this specific guideline does not apply to your work.
Okay, so we're focusing on small molecules and potential damage to the genetic code, which brings us to the core concept, genotoxicity. For you listening, how do we distinguish genotoxicity from just general toxicity?
Well, genotoxicity tests are really specific. They are designed for hazard identification, so detecting compounds that induce genetic damage, focusing specifically on damage to the DNA structure, its sequences, or the chromosomes themselves.
So not just killing the cell.
Right. General toxicity or cytotoxicity might just kill a cell. Genotoxicity is a targeted attack on the blueprint of life.
And the stakes are incredibly high, aren't they? If a compound is positive in this battery, what's the worst-case scenario we're trying to prevent?
We're trying to prevent two major outcomes. First, the compound has the potential to be a human carcinogen. But equally serious, and this is often overlooked, is the potential to be a human mutagen, meaning it could induce heritable effects, via damage to the germline.
That makes the terminology so important.
Yeah.
We often hear two terms related to chromosomal damage, clastogen and aneuploidy inducer. Can you quickly clarify the difference for us?
Absolutely. When we look at assays for chromosomal damage, we are trying to catch two things. A clastogen is an agent that causes structural breakage.
Like it physically breaks it.
Yes. Think of it as physically tearing the chromosome apart. This breakage results in fragments that may not be properly distributed during cell division, and they often form these small extranuclei called micronuclei.
Okay, and an aneuploidy inducer.
Right. So an aneuploidy inducer, on the other hand, it doesn't break the chromosome. It messes up the cell machinery, the spindle, causing the loss or gain of a whole chromosome.
So if I understand correctly, the in vivo tests for chromosomal damage, like the micronucleus assay, are highly efficient because they have the potential to detect both of those things, both the structural damage from clastogens and the numerical errors from aneuploidy inducers all in one go.
Precisely. It's a very effective mechanism detector.
All right, let's transition into the standard practice. If the stakes are cancer and heritable risk, the obvious next question is, what sequence of tests do we actually run? Why do we even need a battery of tests? Why not just one perfect screening tool?
Because that perfect tool, well, it just doesn't exist. No single test is capable of detecting all the genotoxic mechanisms that are relevant to tumorigenesis. The whole goal of the battery is breadth to capture as many potential mechanisms as possible.
But isn't that inefficient? I mean, the guideline explicitly notes that adding mammalian cell tests, while increasing sensitivity, also decreases specificity.
It does.
Meaning we get more positive results that don't actually correlate with rodent carcinogenicity. So why keep the false alarms?
That's the regulatory trade-off, isn't it? We prioritize sensitivity, which is the ability to detect any potential hazard, over specificity. We have to accept the possibility of false positives, because the consequence of missing a true positive, missing a potential human carcinogen, is ethically and medically just unacceptable.
So you manage the cost of those false alarms later on.
Exactly. It's managed later through interpretation, which we will definitely get to.
Okay, that frames the rationale perfectly. Now let's look at the structure. The guideline presents two paths forward, two equally suitable testing options, which is a key concept to memorize. We've called them option 1, the classic, and option 2, the in vivo focus.
And both options are 3-test batteries, and they both start identically. Test 1 is always a test for gene mutation in bacteria,
Really means the Ames test.
which means the bacterial reverse gene mutation test, or the Ames test, yes?
So let's break down how they diverge for the other two tests. Start with option 1, the classic, which uses more in vitro data.
Okay, so option 1 uses one in vitro mammalian test and then one in vivo test. Test 2 is an in vitro cytogenetic test for chromosomal damage. And you have options here. It could be the metaphase chromosome aberration test, the in vitro micronucleus test, or the mouse lymphoma take gene mutation assay, also known as MLA.
So they're interchangeable at that stage.
They are.
And test 3 for option 1.
Test 3 is the mandatory in vivo test for chromosomal damage, and that's typically the micronucleus assay using rodent hematopoietic cells, like from bone marrow or blood.
Got it. So Ames plus an in vitro mammalian test plus an in vivo micronucleus assay. Now, option 2, the in vivo focus, is structurally different because it substitutes that in vitro mammalian test for a second in vivo assay.
Correct. Option 2 moves immediately to the animal model. Test 2 is the in vivo micronucleus assay, just like option 1's test 3. But because we skipped the in vitro mammalian cell culture, we need a third test, a second in vivo test, to make sure 2 different endpoints are covered.
And what does that third test typically cover?
It's a second in vivo assay with a different tissue and endpoint. The most common approach here is a DNA strand breakage assay in the liver, something like the COMET assay.
And why the liver specifically?
Well, the rationale is that the liver is the primary metabolic organ. So if a drug needs to be metabolized to become genotoxic, the liver is absolutely the best place to find that activity.
It's interesting that the regulators allow 2 distinct structurally different paths. It suggests flexibility, but the underlying requirement remains the same. Make sure we cover gene mutation, chromosomal structural damage, and numerical damage with at least one in vivo test.
That's it. Option 2 just kind of front loads the in vivo relevance by ensuring 2 different tissues are exposed in the animal.
And it seems like option 2 is what you'd have to do anyway if you got a tricky positive in option 1.
Often, yes. It mimics the required follow-up if option 1 yielded a positive in vitro result that you couldn't easily discount.
Okay, let's move to the most critical details for implementation.
Yeah.
The numbers. If you're prepping for a test, these dose limits are non-negotiable facts, starting with the easiest one, the Ames test limits.
For the Ames test, the maximum dose is 5,000 micrograms per plate. And remember, when you select your doses, you must ensure that the doses scored show evidence of significant toxicity in the bacteria without going over that 5,000 green ceiling.
Right. Now, for the mammalian cell assays, this is where that famous regulatory ceiling comes in. We need a way for you to remember this. Let's call it the magic millimolar rule.
I like that. For mammalian cell assays, whether it's the MLA or the cytogenetics assays, when you are testing, the maximum concentration you can use, assuming it's not limited by solubility or cytotoxicity, is a hard ceiling. 1 millimolar or 0.5 milligrams per milliliter, whichever is lower.
Whichever is lower.
Yes. If you find genotoxicity above that limit, its relevance is highly questionable.
Why that hard ceiling of 1 millimolar? What's the thinking there?
It's really an attempt to manage those false alarms we talked about.
I see.
When you overwhelm a cell system with a concentration that is, orders of magnitude higher than anything you would ever see in vivo during human treatment, you start inducing nonspecific toxicity, things like high osmolality or protein overload. That can artificially look like genetic damage. The 1 millimin limit helps filter out the most egregious examples of biologically irrelevant noise.
This brings up the next confusing point for students. The acceptable level of cytotoxicity differs dramatically between the assays, even though they're both mammalian. Why is it so different for the MLA versus the standard cytogenetic assays?
It's a subtle but really crucial difference, and it's based on the assay endpoint. For the in vitro cytogenetic assays, looking at metaphase aberrations or micronuclei, the guidance is that cytotoxicity should not exceed a reduction of about 50% in cell growth.
Not exceed 50%.
Correct. If you push past 50% suppression, the risk of getting non-relevant positives due to extreme toxicity or artifacts just skyrockets.
So for cytogenetics, we want to stay under 50% suppression. But the mouse lymphoma assay, the MLA, actually requires us to hit the cells much harder.
That's right. The MLA measures mutation at the T locus. For the mouse lymphoma assay at the top dose, the protocol requires significant toxicity, which is measured as a relative total growth, or RTG, between 20 and 10%.
Which is a lot of cell death.
It is. That translates to about 80 to 90% cytotoxicity. We need to hit it hard because that high toxicity actually increases the MLA sensitivity, allowing it to better pick up certain mechanisms while still retaining biological relevance at that specific endpoint.
So if you're taking a test, remember the split. Cytogenetics, keep it below 50% growth suppression. MLA, you need to aim for 80 to 90% cytotoxicity. That is the necessary nuance.
It really is.
Okay, let's move into interpretation. This is truly the most challenging part of applying this guidance. The goal, as you mentioned, is to assess biological relevance. So how does S2R1 help a toxicologist look at a positive result and confidently say, this is not a human hazard?
This is where the guidance saves drugs. If a result is positive, we use the S2R1 framework to look for clear evidence of non-relevance, what you might call the pitfalls.
Right.
The appropriate in vivo data is the ultimate determinant, of course, but we look for 3 immediate reasons to discount an in vitro positive.
Give us the first 2.
First, statistical significance isn't everything. A positive is questionable if the increase is small and statistically significant, but still falls within the confidence intervals of historical control values for that testing facility.
So if your lab has seen it before, it might just be noise.
Exactly. It's likely just noise, not a drug effect.
Okay.
Second, weak or equivocal responses that are not reproducible when you repeat the test. If you run it again and it's clean, the first result was likely an artifact.
And the third, which loops back to the numbers we just covered.
The third is the most powerful tool. Positives are considered of questionable relevance if they happen only under conditions that do not occur in vivo, and specifically if they occur only at those high toxic concentrations.
Of thresholds.
Precisely. We have rules here. An MLA positive seen only when cytotoxicity is greater than or equal to 90%, or a cytogenetics positive seen when growth is suppressed by more than or equal to 50%.
Let me use a hypothetical scenario to ground this for everyone listening. Imagine a new compound, drug X, works beautifully in phase I. It tests negative in the Ames test, and in the cytogenetics test, staying below 50% toxicity, it's also negative. But in the MLA, it only shows a positive mutagenic signal when you push the concentration so high that 95% of the cells are dead. Why does S2R1 potentially save drug X?
It saves drug X because that positive signal is happening in a cellular environment that is completely non-physiological. The toxicity itself is likely driving the apparent genotoxicity, maybe through oxidative stress or metabolic chaos, not the drug's intended molecular mechanism.
So it's an artifact of the conditions.
Yes. Since the increase occurred only above that 90% cytotoxicity threshold, a toxicologist has the regulatory basis to categorize it as a non-relevant positive.
That makes those toxicity limits functionally important for the viability of the drug itself. Now, let's flip that coin. If we get an in vitro positive and we can't rule out the relevance, meaning it didn't hit those extreme toxicity thresholds, we move in vivo. If we get a negative result there, how do we know that negative result is trustworthy?
This is perhaps the single most important concept in the whole guideline.
Okay.
The value of a negative in vivo result is directly tied to the demonstration of adequate exposure of the target tissue. A negative result is meaningless if the drug never effectively reached the bone marrow or the liver cells.
So how do we prove adequate exposure? What's the method?
We use 2 primary methods, and often both. Method 1 is by demonstrating target tissue toxicity. For the in vivo micronucleus assay, for instance, we prove exposure by observing a significant change in the proportion of immature erythrocytes, or PCEs, in the bone marrow or blood.
Wait, why is a change in PCEs proof of exposure? How does that work?
Well, the micronucleus assay requires rapid cell division to detect damage. If the compound reaches the bone marrow and is toxic, it slows down the production of those new red blood cells.
Ah, I see.
So if we see a drop in the PCE to total erythrocyte ratio, that is physical evidence that the drug got there and disrupted cell turnover. We look for a similar reduction in the mitotic index for aberration assays.
Perfect. Toxicity proves the compound showed up for the test. What's method 2?
Method 2 is measuring drug-related material directly using toxicokinetic, or TK, data. You can measure the compound's concentration in the blood or plasma. Since bone marrow is highly perfused, blood levels usually suffice as a surrogate for exposure. However, for tissues like the liver, which we often test with the COMET assay, the guideline strongly encourages directly measuring the drug in the target tissue itself to ensure it's really present.
And what if it's not?
If systemic exposure is poor, we may need to increase the dose, change the administration route, or even select a different animal model.
And finally, if we have a positive in the mammalian cell assays, but a negative Ames test, and we can't discount the relevance based on those toxicity thresholds, what's the standard follow-up required by the guidance?
If the relevance remains an open question, the standard follow-up is to mirror option 2 of the standard battery. You conduct 2 appropriate in vivo assays in different tissues with assurance of adequate exposure for both to definitively prove the lack of in vivo activity.
So you basically run the full option 2 battery.
You do. That provides the highest regulatory assurance.
This has been a tremendously dense and critical deep dive. For you listening, if you need to memorize this for a meeting or a test, let's distill this into 5 absolutely critical points, the things you must remember about ICH2R1.
Okay. First, the S2R1 goal. It's all about harmonizing genotoxicity testing to predict human carcinogenic and heritable risk from new small molecule pharmaceuticals.
Second, the standard battery requires 3 tests and offers 2 equally suitable options. Remember the mnemonic. Option 1 is heavy on in vitro testing. Option 2 is heavy on in vivo testing, always including a second in vivo assay in a metabolic organ like the liver.
Third, know the maximum dose limit for mammalian cell assays. The ceiling is that magic millimolar rule. 1 millimolar or 0.5 milligrams per milliliter, whichever is lower.
Fourth, remember those crucial toxicity thresholds that define relevance. A positive result must be questioned if it occurs only above the strict limits, greater than or equal to 50% growth suppression in cytogenetics assays, or greater than or equal to 80–90% cytotoxicity in the mouse lymphoma assay.
And fifth, the core concept of risk management. A negative result in an in vivo test is only trustworthy if adequate exposure of the test compound to the target tissue is successfully demonstrated, usually via cytotoxicity like that PCE ratio drop or toxicokinetic measurement.
That distinction between the in vitro test identifying a potential hazard and the in vivo data determining its biological relevance, that really is the key philosophical shift this entire guideline represents.
It is.
Essentially, if the drug didn't even knock on the door of the cell effectively, we can't trust the cell's negative answer.
It's the constant challenge for the toxicologist, avoiding unnecessary program termination because of high-dose artifacts while never, ever compromising safety. It requires scientific rigor and regulatory savvy.
An excellent thought to end on. Thank you for guiding us through this essential document.
My pleasure.
And thank you for joining us on this deep dive. See you next time.